Hey guys, today I'm going to be giving you a pretty big overview of stellar evolution. Now, let's start off with main sequence stars because that's where stars start. Main sequence stars are stars that have not run out of hydrogen fuel. Main sequence stars usually have properties that can be more or less predicted by their mass and metallicity using the Hertzsprung-Russell diagram. The luminosity of a main sequence star is between mass over mass of the Sun to the third and mass over mass of the Sun to the fifth, but almost always between mass over mass of the Sun to the 3.5 and mass over mass of the Sun to the 4. The reason I didn't say that it's just one line is because it's much more of a range, and it can sometimes differ by a factor of 10 depending on the specific composition and properties of the star as well as the age. Stars will spend 90% of their time in the main sequence star. The stellar radius of a main sequence star is between mass over mass of the Sun to the 1/2, meaning the square root, and mass over mass of the Sun to the 1, but is usually between mass over mass of the Sun to the 0.6 and mass over mass of the Sun to the 0.8. The temperature of the star can be calculated by the formula luminosity in watts over the Stefan-Boltzmann constant times the surface area of the sphere, which is 4 pi r squared, to the 1/4. Remember to do the radius in meters and not kilometers, because meters is an SI unit. It is proportional to the temperature of the Sun times the luminosity over the radius of the star relative to the Sun squared to the 1/4. And this is all relative to the Sun, so you have to multiply it by the Sun's temperature, which is 5,778 degrees Kelvin, or 5,505 Celsius. But Celsius does not start at 0 temperature, so it won't work. Here you can see this helpful chart from Wikipedia, and it shows typical main sequence stars and their properties. And now here we have these formulas in a spreadsheet that I've made that calculates the properties of main sequence stars. A2 is mass, and everything is relative to the Sun except temperature, which is just in Kelvin. By the way, this is radius. This is temperature, where D2 and B2, D2 is the luminosity and B2 is the radius. This is luminosity relative to the Sun. I know it's kind of a wacky formula, but you know it goes here and there, so. This is the lifespan in years, because different stars will burn different amounts of fuel to burn different amounts of energy, because more massive stars won't stop at burning hydrogen and will burn a lot more massive stuff, so they can burn for longer than you might expect given their mass. And I also conveniently have this Hertzsprung-Russell diagram here for you to look at. So TLDR, main sequence stars get bigger, brighter, hotter, more violent, and shorter lived the more massive they get. But it's important to note that these star colors you see in the diagram are kind of inaccurate, because the K-type stars are more of a pale yellowish orange than an orange, and the G-type stars are usually either very, very pale yellow or almost always white with like a hint of green or something else. The F-type stars are white with a hint of turquoise or cyan, and the A-type stars are white with a hint of cyan or blue. The B-type stars are where it starts to get really blue, and the O-type stars, basically you get fried before you even look at them. So here you can see post-main sequence stars. No simple formula can predict post-main sequence stars, which is why we have the Hertzsprung-Russell diagram. Stars above about 0.3 to 0.5 solar masses will spend 10% of their times in the post-main sequence phase. But stars lower than that mass, first of all, the universe hasn't existed long enough for them to exit the main sequence phase. That's true for any star less than about 0.9 solar masses. And second of all, they don't really ever exit the main sequence phase because they aren't massive enough to fuse anything other than hydrogen. So basically they'll just be like tiny little hot main sequence stars called blue dwarfs, which is funny because they're not blue main sequence stars. They're basically just tiny blue main sequence stars, if you want to think of it that way. I'm just going to write that down for you so you can see it more clearly. 0.5 to 8 solar mass stars will become yellow to red giants, and between 1 and 8 solar mass may spend short periods as supergiants. Stars between 8 and 25 solar masses will become blue giants and red to blue supergiants, and some stars between 15 and 25 solar masses may become red hypergiants. At between 25 and 40 solar masses, stars stop working like normal and burn in only 5 million years. Stars in this mass range will become blue giants, but will quickly become blue to white supergiants and eventually become blue to yellow hypergiants. Now let's talk a little bit about the types of fusion that happen inside of stellar cores. So for brown dwarfs, which are from 1/100th to 8/100ths of a solar mass, it can only fuse hydrogen to deuterium and then to helium-3 and 4, but much of the helium-4 will photodisintegrate before it can refuse back into helium-4, so mostly helium-3. From 0.08 to 0.5 solar masses, stars can only fuse hydrogen into hydrogen, deuterium, and tritium, as well as helium-3, and then produce helium-4, so it can't go any further than that. From 0.5 to 8 solar masses, it goes from hydrogen to hydrogen, deuterium, tritium, and helium-3, to helium, and then to carbon, nitrogen, and oxygen, which takes the form of a white dwarf because the outer layers have been blown away by the intense radiation. Then, from 8 to 10 solar masses, things get a little interesting. So it goes from hydrogen to deuterium, tritium, and helium-3, then to helium-4, then to carbon, nitrogen, and oxygen, then to oxygen, neon, and magnesium, and then either it becomes a white dwarf or a neutron star. If it becomes a neutron star, there will be a supernova. From 10 to 21 solar masses, it goes all the same as 8 to 10, except after the oxygen and neon and magnesium, it goes to silicon, sulfur, and calcium, then chromium, iron, and nickel. Then it collapses into a neutron star, creating an extremely powerful supernova. Then, from 21 to 40 solar masses, it gets crazy, because at the end, basically, the neutrons and protons in the neutron star themselves can't hold up against the gravitational forces, causing it to collapse into a sea of quarks where time dilation is so absolute that pretty much no light can escape. But because the time dilation is so strong, it can never become 100% a black hole. It can only become 99.999999 and 4 million more 9% black hole. Then from 40 or more, it does all the same, except when it explodes, who knows what it's going to do? There could be nothing. There could be just a piece of neutron star. There could be a black hole. There could be a smaller black hole. There could be a collapsar with rotating jets. Who knows? So iron is a little bit complicated, but I'll try to sum it up for you. So iron, once it's produced in the core of a star, it can't fuse with most other elements that are likely present in the core to produce a net release of energy. You could theoretically fuse it with lighter elements like hydrogen and helium to produce energy, but that's pretty big stretch, and there isn't going to be any of that in the core. And even if there was, the Coulomb barrier would be so strong that it wouldn't even want to fuse anyway.